This topic is a little unusual because it includes both sections 2.3 and 2.6. The reason for that is that we're learning a new technique using a theorem called the Squeeze Theorem that applies both to limits as x approaches a finite value and infinite values. So let's see, what happens if we try to find the limit as x approaches infinity of cosine of x? Well, if you remember, the graph of cosine, similar to the graph of sine, right? It just keeps oscillating. Well, so we know that the limit does not exist. Because f of x, cosine of x, never settles on a value as x increases. Right? As it increases arbitrarily, right? What if we consider this limit? Well, we should remember from last section that that's going to give us 0. Numerator is 1. It's a constant. X is blowing up, so of course 1 plus x to the sixth blows up tremendously, and we get 0, right? Doesn't mean the function ever equals 0. It doesn't. But it does get arbitrarily small. It gets arbitrarily close to 0 if you go far enough. So then the question, I guess, is what happens if you combine the two? All right, well, I guess we have to kind of do what we often do, and bust out Desmos, right? Use the graph, maybe use a table or something. I think here the graph will suffice, right? So if we just let f of x, do that. Turn that keyboard on. Let f of x equal cosine of x divided by 1 plus x to the sixth, right? Now, looking at this, I guess it's kind of clear what's happening, right? Looks like we're approaching 0. It looks like we're approaching it pretty quickly, right? So it doesn't really look much different from if we had, from the first problem, or from the second problem, right? It looks like the answer is going to be 0. The question is why? Well, the reason is because of something called the Squeeze Theorem. Now, before I formally define the Squeeze Theorem, I would like to illustrate it in the following way. Cosine oscillates, but it doesn't oscillate by very much. You might remember that the lowest value that cosine can possibly take is -1, and the highest value it could take would be 1. So if I go ahead and call this g of x, for reasons that'll be clear in a couple of minutes, what if we let f of x equal, instead of cosine of x, let it be -1 over 1 plus x to the sixth? This is the same thing, but I just want to emphasize that we're replacing cosine with -1. And then I'll let h of x equal +1 over 1 plus x to the sixth. Okay, so some kind of weird stuff happens at first. Let me actually just, these are not quite as important. They're not the function we're actually looking at, so I want to make them dotted, so to speak. But I do want to point out that g of x gets no lower than f of x and no higher than h of x. And look what happens to those guys. Right? As you can see, g of x is always in between both of them, right? The red is always in between them, right? But look at that. They all approach 0. Maybe some approach from the top, some approach from the bottom, but they all approach 0 as x gets arbitrarily large. Even though g of x remains, well, if we zoom in enough, it always remains in between them, right? See, if we zoom in enough, look at that. Sure enough, h of x is still always above g of x, which is always above h of x. Right? It's always bounded by these two. So the idea is that, well, if h of x and f of x have the same limits at infinity, well, then so should g of x. Okay? So that's the limit, or that's the reasoning behind the Squeeze Theorem. So more formally, how would we state this? Well, first let's just state the answer. Well, just kind of tentatively. Here's what it says. The squeeze theorem says, suppose the functions f and g and h satisfy f of x is less than or equal to g of x, which is less than or equal to h of x near a, which is what we're considering, right? Where a is a real number or it's plus or minus infinity. Then the following is true. If the limit as x approaches a of f of x equals a limit as x approaches a of h of x, and that limit exists, then the limit as, I don't like this extra then. Limit as x approaches a of g of x also equals L. Okay? That's the formal statement of what we were saying earlier. Let's just get rid of that ugly then. I don't like that. If then. All right, so let's take a look. We have to find functions f and h so that cosine of x over 1 plus x to the sixth is between them, right? F of x needs to be a lower bound, h of x needs to be an upper bound. We also need for their limits to be the same at infinity. And they need to exist, right? If there are infinite limits for some reason, that won't work. Or if they're different limits, then that won't work. The squeeze theorem is a little bit different because it's not just a technique. It's a theorem that you have to verify. It's a multi-step process, but it is formulaic, right? So if you can understand the process, then you'll probably be fine. So let's take a look. The key thing that makes this problem difficult is the trig function. So that's what we start with. Now, if we're talking about sine and cosine, then we always know that sine and cosine are between -1 and 1. So that's what we start with every single time. Then we just manipulate the inequality until we get the original expression. So I need to divide by 1 plus x to the sixth. So if we want cosine of x over 1 plus x to the sixth, well then I guess I have to do that to both the right side and the left side. And maybe now it's a little clear how earlier in the graph I came up with those functions 1 over x, 1 plus x to the sixth, and -1 over 1 plus x to the sixth. This is our f of x, this is our h of x. Now what we need to confirm at this point is that the limit as x approaches a of f of x equals the limit as x approaches a of h of x, and they both exist. But this is true. Limit as x approaches infinity of -1 over 1 plus x to the sixth equals limit as x approaches infinity of +1. It doesn't matter. The numerator is constant. Denominator is blowing up, so our function approaches 0. So check, yay. They equal each other and the limits exist. And then we write by the squeeze theorem. All right, we write by the squeeze theorem. We have that the limit as x approaches infinity of, in this case it's cosine of x over 1 plus x to the sixth, equals 0, right? So we do have to find two limits, but we get that the third one exists for free because of the squeeze theorem. So that's the real way that we do this problem. Right? We don't look at the graph, we don't use reason, we use squeeze theorem, right? Formally use the squeeze theorem. Let's take a look at a couple more examples. Find this mess of a limit using the squeeze theorem. Barf. Actually not that bad. even as nasty as something looks, you just always hone in on the trig function. Now, you can say that that sine squared of x is between -1 and 1, but it's slightly more astute to note the following. I'll just say note that because it's squared, it's non-negative. So 0 is actually less than sine squared of x, less than or equal to sine squared of x, which is less than or equal to 1. All right? So from there, we're just going to manipulate this until we get this. So we're going to have, I'm just going to add 2 to everything, right? 2 is less than or equal to 2 plus sine squared of x, less than or equal to 3, right? 2 plus 1. And then just, I'm going to put an imply symbol. Just means sort of this implies that, implies the other thing. I'm going to multiply everything by x squared. Right, it's looking a little more familiar. Hope you agree. And then at this point, rather than writing it all out again, I'm just going to, divide everything by x cubed plus 100. And now we have exactly what we started with. Lovely. So now what we have to confirm is that the limit of this guy as x approaches infinity equals the limit of this guy as x approaches infinity. And it turns out they do. So actually what I'm going to do, kill 2 birds with 1 stone, I'm going to write since the limit, I know they're going to equal each other because they better equal each other or else this whole thing didn't work, right? Well, see if I can do this in one shot, right? This limit, which you might notice is infinity over infinity, so we need to knock it down a little bit, equals this, x approaches infinity of 2 over x plus 100 over x squared, which equals 0. And similarly, limit as x approaches infinity of, well, that's an infinity, 3x squared, right? We're doing the exact same thing here, right? Right, again, we have to divide by the lower degree leading term. See how it's exactly the same thing? We're just replacing a 2 with a 3. Right, so since the lower bound limit at infinity equaled the upper bound limit at infinity by the squeeze theorem, right, because we would never forget to mention the squeeze theorem or we would get knocked down to a progressing, we have limit as x approaches infinity of, what was the, x squared times 2 plus sine squared of x all over x cubed plus, is there more just writing exercise, 100 equals 0, right? Done. So it may have looked a little more complicated. We may have had a couple more algebraic steps, but the reasoning was exactly the same. And I don't think the actual limit-taking process was a whole lot more difficult than before. Maybe you disagree. Now let's take a look at this guy here. Similar sort of thing. Now, one thing to note is that we have something inside the parentheses. That does not affect anything. So I'll say note that -1 is less than or equal to, and you can just put right, we have a negative sign in front, just put it there. No need to make things complicated. All right. In case you're wondering, the thing inside the parentheses makes it oscillate quicker and quicker and quicker, but it doesn't affect the height. It doesn't affect the amplitude. That would be if we put a 3 on the outside. Okay, but we didn't. Right, so what we have, maybe I'll put it over here. So, 5x minus 1 less than or equal to 5x minus sine of this lovely stuff right here, less than or equal to 5x plus 1. All that Lovely, lovely stuff, right? And then, of course, we divide. Okay. And once again, right, assuming we did everything correctly, I'm not going to throw you some weird curveball of a problem. The left and right-hand limits should equal each other, and they should exist, right? So I'm going to write, since the limit as x approaches infinity of this thing, right, which, you know, a little annoying, right, because it does equal infinity over infinity, so we do have to knock it down a peg, divide by the higher power, or the, you know, leading term, and this is going to equal limit as x approaches infinity of 5 minus 1 over x all over 1 plus 27 over x equals 5, and maybe I'll write that on the bottom here, and I'm just going to cheat a little bit here and do a little bit of copyage here. A little copy paste. Maybe I'll move it down a little bit. Down a little bit. And then just turn this minus into a plus. Right? We get the same thing by the squeeze theorem. We have that the limit as x approaches infinity of 5x minus sine of 3x all over x plus 27 equals 5 as well. So just to show you, we don't always have to have a limit of 0, right? Here we had a limit of 5. Same reasoning. We're still using trig functions, but we had a different limit. All right? And here's another example, and note that in this case, we're not approaching infinity or negative infinity. We're approaching 0. So let's consider this one, right? X approaches 0, x squared cosine of 2 over x. Now, if you were just looking at cosine of 2 over x, that's one of those crazy oscillating functions that oscillates more and more the closer we get to 0. It doesn't exist in and of itself. Limit as x approaches 0 of x squared equals 0. So the question is, which one wins out? Now, if the limit really doesn't exist, then we can't use the squeeze theorem. So hopefully something will work. Well, again, we're going to start with the trig function. As crazily behaved as cosine of 2 over x is towards 0, it never is greater than 1 or less than negative 1. So we have the same bounds as before. So if we multiply by x squared, well, look, we have the original function. And we're looking pretty good, right? Because maybe you can see this, but since limit as x approaches 0 of negative x squared equals the limit as x approaches 0 of positive x squared, I think this is quick enough to see that we get 0 by the squeeze theorem. We have that the limit as x approaches 0 of x squared cosine of 2 over x equals 0. Right? So I guess the answer in this case did equal 0. But just pointing out that, it doesn't always have to equal 0, and here x was not approaching infinity.